Hi everyone, in this video we are going to solve a problem about work and energy. In the following system, a ball is moving with a velocity of 40 meters per second in a position A, this position. The distance between A and B is 2.5 meters, this distance. There is friction between position A and B, so in this region we have friction. The kinetic friction coefficient is 0.4. The height in B is the height in C is 1.5. The mass of the ball is 10 kilograms. Okay, and then we have questions about the velocity in A, B, C. Then questions about the kinetic energy, so the change in the kinetic energy between A and B and between B and C. These are the items B and C. D, obtain the change in the mechanical energy between A and B and the change in the mechanical energy between B and C. And obtain the work of the conservative forces between A and B and between B and C. Okay, before we solve the problem, just a brief review of important concepts. Work of a constant force. We are working with forces that are not changing in time. So the work of a constant force in a certain displacement, for example, between position A and B, as in initial position A, final position B, for example here, is the absolute value of the force, the absolute value of the displacement. The displacement is final position minus initial. In this case, if we begin with a frame of reference with position A equal to 0, suppose that the initial position is 0, we consider positive to the right, position B is 2.5 meters. So the displacement will be 2.5 minus 0 equal to 2.5. Okay, well, and then we have the cosine of an angle. What is the angle? The angle between the force, each particular force, and the direction of motion, okay, which is the displacement. Or from the displacement we have the direction of motion. No? Theorem. Then we are going to apply the theorem of work and kinetic energy, which states that the sum of the works is equal to the change in the kinetic energy, the sum of each individual force. So if the object, in this case the ball, is under the effect of three forces, the work of force 1 plus the work of force 2 plus the work of the third force is equal to the change in the kinetic energy, which is final kinetic energy minus initial. Final kinetic energy is 1/2 of the mass velocity final square minus 1/2 of the mass velocity initial square. You can apply this theorem between between the two positions that you want. In a moment, we are going to solve the problem splitting the total motion between A and B. That's because that's an horizontal motion. And then between B and C, because here between B and C we have no friction and there is a change in height. Therefore, we are going to split the problem in two stages. Okay, well, other expression of the previous theorem. The theorem of work and kinetic energy could be written in a different way, splitting the non-conservative forces and the conservative forces. In the frame of this exercise, the conservative forces, we have only one, actually, the weight. And the other forces, like normal force, friction, or tension, if we have a rope, for example, a string, these are non-conservative forces. So if we rewrite this theorem, we can obtain this one, that is the sum of the works of the non-conservative forces is equal to the change in the mechanical energy. Pay attention that it's not equal to the kinetic. No, mechanical energy is kinetic plus potential. We have it here. No, mechanical energy is kinetic plus potential. Just a review. So the sum of the works of the non-conservative forces is equal to the change in the mechanical energy. So if you work between two different positions, the final is the second position, the initial is the previous one. So we have kinetic energy final plus potential energy final. We're going to apply this theorem in the second part of the exercise. And in a minute we discuss why. Minus the sum, minus the mechanical energy initial. The final mechanical energy is the final kinetic plus the final potential energy minus the initial kinetic energy plus potential initial. Okay, well, now we solve the problem. We are going to discuss what is happening in this problem. Well, we have two parts. Between A and B, we have friction and we have an horizontal problem. First of all, read carefully the statement of the exercise, write the information that you receive. The initial velocity A is 40 meters per second, the mass is 10 kilograms, the friction coefficient, in this case dynamic or kinetic, because the object is already sliding in this surface, the displacement between A and B, because we have here there is friction between A positions A and B. The kinetic friction is 0.4. The height in C, as I said before, is 1.5. The mass of the ball is 10 kilograms. So we have the information here in this box. Okay, what happens between A and B? When we analyze the ball in this path, and we have, I don't know, a position here, an intermediate position, the forces acting on the object are the normal force. So first of all, we find the weight, no, the gravitational attraction, that's the weight. Then the surface below exerts a normal force. There is no forward force, no, because the ball had a previous impulse, okay, a previous interaction that now is not present. So someone, for example, someone kicks a ball, or we have a cannonball and the ball is fired. I don't know. So the impulse is or accelerated the ball at a certain instant, but now there is no forward force. The only force present in the direction of motion is friction, but is in the opposite direction. Okay. So we have three forces: friction, the normal force, and weight. That's what we have here again. Okay. Okay. So the forces acting on the object are the weight. Weight is mass times gravity, mass 10 kilograms times gravity 10 meters per second square if we round it, because the real value is a little bit lower now, 9.8, but we use 10. So the weight is 10 kilograms times 10 meters per second square, 100 Newton. Okay, that's the first force. The second force is the normal force. The normal force is, how do we obtain the normal force? Well, first of all, state a frame of reference. Here we use positive to the right in the horizontal coordinate that we call x, positive upwards in the vertical direction. We call this axis y. So one possibility is to sum the forces in y. So normal minus weight is equal to 0. So the absolute value of the normal. No, the normal we are going to consider it positive because it points upwards. Weight negative because it points downwards. So the normal force is equal to the weight, and we know that the weight is 100. So now we have the normal force, that is also 100 newtons. In this frame of reference, normal 100, weight minus 100 newton. Okay, according to the frame of reference, you can obtain the weight that is minus 100 newton. Okay, what about the friction? In a minute we are going to use the friction, but remember that friction is the dynamic kinetic friction coefficient. In this case, is a situation where the object is already sliding, so you need the kinetic or dynamic friction coefficient times the normal. Okay, in this case, 0.4 times 100 newtons, so the friction force is 40 newton. Okay, so now we have the three forces. We are going to use them in a minute. Okay, what is the goal of this part? If we read carefully the statement, obtain the velocity in positions B and C. We are going to obtain the velocity in B. And we are going to apply the theorems. Therefore, we need the kinetic energy in A, the potential energy in A. What happens with the potential energy in A? Check that mass, gravity, height in A, but what happens with height? If we use a frame of reference here, and we use this level like the 0 in height, well, the height is 0, so the potential energy in A is 0. And what happens with the kinetic energy? The kinetic energy is 1/2 of the mass, velocity in A squared, 1/2 of 10 kilograms, the mass was given, times 40 meters per second squared. 1 half times 10, 5 kilograms, 40 meters per second times 40 meters per second, 1,600 meters square second square. Remember that kilogram, meter square, second square, this unit has a name that is Joule, the unit of energy. We multiply 5 times 1,600 is 8,000 joules. So now we have the three forces that are acting between A and B, the kinetic energy, the potential energy. Well, if we check the theorems, the one that is useful to solve this problem, to find the velocity in B, is the first one. The sum of the works is equal to the change in the kinetic energy. Okay, which are the forces acting? Remember that we are working between A and B, okay, from A to B. The work of the weight plus the work of the normal plus the work of the friction is equal to the change in the kinetic energy between positions B and A. So the kinetic energy in B minus kinetic energy in A. The work of the weight is the absolute value of the weight, the absolute value of the displacement, cosine of the angle between the weight and the direction of motion. But if we analyze the motion, check what happens. We have weight and the direction of motion is to the right because position A is here, position B should be here. So we can consider this angle that is 90 degrees or this angle that is 270. In both cases, the cosine of 90 is 0. So the cosine of 90 is 0. So 0 times the weight that we know the value of the displacement, but the whole term is 0. The same happens with the normal force. The normal force in this problem, or between A and B, is perpendicular to the direction of motion, that is to the right. So the angle that we consider for the normal force is 90. So the cosine of 90 is 0. 0 times the value of the normal force times the displacement. So we can cancel the whole term, 0. And we have the work of the friction. The work of the friction is not 0. Check that friction points to the left. Okay, friction is in this direction. So the angle that we must consider is this one, 180. This angle is 180. The ball is rolling to the right, the friction is to the left, 180. So now we replace absolute value of the friction, absolute value of the displacement, cosine of 180. And that should be equal to final kinetic energy, in this case the kinetic energy in B, minus the kinetic energy in A. Kinetic energy in A, we already have the value, 8,000 joules. The kinetic energy in B, we don't know, 1/2 of mass velocity B squared. The velocity B is the variable that we don't know and we want to find. Kinetic friction is 0.4, the normal. This is the friction. We already obtained the value, 40 newtons, or 0.4 times 100 newtons. The displacement is 2.5 meters, because the displacement is final position minus initial, and as I said before, is 2.5 meters minus 0 meters, okay, 2.5. And the cosine, and without sign, but this one is positive, so there is no problem, 2.5. Cosine of 180 minus 1, and now we multiply 40 times 2.5 times minus 1 minus 100 joules. So the sum of the works, and check something that is useful for the following items, the sum of the works in this case is equal to minus 100 joules, because you have 0, 0, minus 100. So minus 100 joules is the sum of the works and is equal to the change in the kinetic energy. That's the answer for the following item, the item C. Obtain the change in the kinetic energy between, for item B, obtain the change in the kinetic energy between A and B. So now you have the answer for the item B. The change in the kinetic energy is minus 100 joules, the sum of the works. Okay, but now we are going to obtain the velocity in C, B, sorry. We have to finish this part. So we are here. 1/2 of the mass, velocity in B squared. 1/2 of 10 is 5, minus 8,000 joules. We pass 8,000 to the left, adding minus 100 plus 8,000, 7,900 joules. And then we pass the 5 kilograms dividing, okay? 7,900 joules divided by 5 is 1,580. Okay, 1,580. What about this unit, joule divided by kilogram? Joule divided by kilogram is Newton meters, joule divided by kilogram. Newton is kilogram meters per second square times meters divided by kilogram. We cancel the kilograms and we have meter times meter square divided by second square. Okay, and now we obtain the absolute value of velocity v passing the square root, or the square into a square root. So the square root of 1,580, you apply the square root to the number and to the units, and we obtain 39.75 meters per second. That's the velocity in v, the second velocity. So in item A, we need the velocity in v and velocity in c. Velocity in v already obtained. Then velocity v, change in the kinetic energy. We discussed it. It's the sum of the works, so minus 100 joules. Okay. What about items D and E? In item D, obtain the change in the mechanical energy between A and B, and then between B and C. We are going to answer between A and B. Change in the mechanical energy. The change in the mechanical energy is the mechanical energy in B minus mechanical energy in A. Mechanical energy in B is the potential, gravitational potential energy plus the kinetic energy in B minus the potential energy in A plus kinetic energy in A. But what happens between the heights? The heights are zero because the problem is horizontal. So in both positions, A and B, the gravitational potential energy is zero. So we have kinetic energy in B minus kinetic energy in A. And that's the change in the kinetic energy. And we know the value, minus 100 joules. If you want to check that the result is minus 100 joules, you can replace the mass, 10 kilograms, velocity in B, the mass again, and velocity in A again, and you obtain the same result. Okay? Well. And the last question is obtain the work of the conservative forces between A and B, between B and C, but we are analyzing A and B. The work of the conservative forces is 0 joules. Why? Because the work of the conservative forces is the work of the weight, and we discussed previously that is 0. Okay, now, what happens between B and C? Between B and C, okay, remember that the problem is here, what we want to answer. So, what happens between B and C? Okay, so the ball had in A 40 meters per second. That was the velocity. Then, due to friction, part of this kinetic energy is lost, perhaps because it is transformed into heat. Here, friction, like energy is transformed into heat, sound. And now, in B, the velocity of the ball is 39.75 meters per second. 75 meters per second. Okay? We have it here. And what happens when the ball tries to climb this like tiny mountain? No, it's not a mountain, but this slope, okay? This inclined plane. Well, what typically happens is that part of the kinetic energy, because it has energy due to or the energy related to motion, is transformed into potential, and the velocity decreases. That's what we typically know. So the velocity in C should be lower, and the idea is to find the value. Okay, so what happens between B and C? First of all, we analyze the forces here, okay? Which are the forces? There is no friction. So between B and C, the typical convention is that if we don't draw these segments, the idea is that it has no friction. It is like moving in a surface with ice, for example. So the ball has velocity, so due to inertia, it keeps on moving because it has velocity. And the forces acting on it are the weight downwards, the normal force perpendicular to the surface. So remember that weight is a conservative force, and if we analyze the angles for the theorems, the direction of motion is parallel and upwards to the surface. The normal is perpendicular. So the angle that we have to use in the work of the normal is 90 degrees. But we know that 90 degrees. So we know that the work of the normal will be 0. Like what happened in the previous part between A and B. So the work of the normal is 0. The work of the weight is not 0, but the problem is that we don't know this angle. In a different kind of exercise, if we receive the angle, we can find or we calculate the work of the weight. But in this case, we cannot calculate the work of the weight directly. So we keep on working. But we have a possibility. The possibility, because you would say, well, why could we apply the previous problem, but in the previous theorem? In this case, not directly, because the work of the weight, how do we obtain the work of the weight? We don't know. So one possibility is to use the previous theorem and remember that the work of the weight is equal to the change in the minus the change in the potential energy. That's a possibility. But we are going to, instead of applying the first theorem, we are going to apply the second one. That is this one. The sum of the works of the non-conservative forces is equal to the change in the mechanical energy. To solve this problem is a little bit easier. In a minute you will see. Okay? Check this. If we apply the theorem, there are two forces acting on the object, the normal and the weight. The normal is non-conservative. The weight is conservative. So in the sum of the works, we have a 0 because the only non-conservative force is the normal, but the work of the normal is 0 because it is perpendicular to the direction of motion. So the cosine of 90 is 0. So the sum of the works of the non-conservative forces is 0. That means that the change in the mechanical energy between B and C is 0. So we would say that the mechanical energy is conserved between B and C because the value is constant. So the mechanical energy in B is equal to the mechanical energy in C because if you subtract them, you obtain a 0. So the final mechanical energy, that is the mechanical energy in C, minus the mechanical energy in B, that's 0. So both are equal. And now we obtain the velocity c, that is our variable that we don't know. One possibility when you write the theorem, well, first of all, check that you have the whole set of terms, no? Potential energy in C, kinetic energy in C, minus potential energy in B, kinetic energy in B. Potential energy in B is 0 because B is the lowest point, B is this point, C is this point. So if we consider height from here, this height is 0 and this height is given, that was 1.5. Here 1.5 meters, but think about this, no? Height. Okay, in this equation, if we have the four terms equal to 0, we cancel the one of the height b because height b is 0. So we have three terms: potential energy in C, kinetic energy in C, and kinetic energy in B. And remember that we have a minus because it is a change in energy, in this case mechanical. We can cancel the masses because it's an identical term that multiplies each term. So mathematically we can cancel it. And now we have gravity hc, height c, 1/2 velocity c squared minus 1/2 velocity v squared. Remember that the value that we don't know is this one. So we pass gravity height to the left, minus 1/2 velocity v squared to the left, one subtracting, one adding, and then we have this 1/2 that is going to pass dividing. And then to obtain the absolute value of the velocity c, we pass the square root. And the last step is to replace gravity 10 meters per second squared, but check that you had a minus because this term was in the right side before. The height c is 1.5, no? It was given. The velocity v, that is what you obtained previously in between a and b, and 1/2 multiplied. Pay attention that this term is square, so 39.75 squared is 1580 meter square second square times 1/2. Okay, and 10 times 1.5 is 15. And we have a 1/2 dividing. To divide by 1/2 is the same as to multiply times 2. So we have 1/2 times 1580 is 790 minus 15 times 2 is 1550. And the square root of this number is 39.37 meters per second. And that is the final velocity, velocity c. So with this, we complete the item A because we need, we obtain velocity v, velocity c. Then obtain the change in the kinetic energy between the change in the kinetic energy and between obtain the kinetic energy between B and C. And we have to answer this. Change in the kinetic energy between B and C. Okay. In a minute, we are going to answer. The change in the mechanical energy, we said that is 0 because it's the sum of the works of the non-conservative forces. The work of the weight, you cannot calculate it directly because you don't know the angle, but we know that it's the minus the change in the potential energy. And the change in the potential energy is mass gravity final height minus mass gravity initial height, that is height b. This height b is 0. So we replace mass gravity height, mass 10 kilograms, gravity and height 1.5, and the work of the weight is minus 150 newton. And we have, and here, what does it mean? The work of the weight is minus 100 newtons. The change in the potential energy is 150 joules. Sorry, not newtons, joules. 150 joules. And what about the kinetic energy? If we know that the change in the mechanical energy is 0, when we sum these two terms, the result should be 0 because what you gain in one energy must be lost in the other one. So the total, the mechanical energy, the change is 0. So the kinetic energy, the change in the kinetic energy should be minus 150 joules. If you want, you can also calculate this value like 1/2 of the mass, velocity final, in this case velocity c squared, minus 1/2 of the mass, velocity in b squared initial, no? Because we are comparing b and c. And you'll check that you obtain the same result. Well, with this, we finish this exercise. If you have questions, ask me in the or post them in the commentaries of this video. Thank you very much.